What if you could patent a body part? From wooden peg legs to mind-controlled bionics, the inventions that rebuilt us tell a wild, very human story. Welcome to Patent Oddities, the show where the brilliant, the bonkers, and the barely believable collide in the patent office. Today, we're stepping into a lineage of invention that's as intimate as it gets: prosthetics. It's a story older than paper and more personal than any gadget on your desk. Because when engineers and amputees collaborate, they're not just making devices, they're rewriting what a human body can do. We'll trace this arc from the earliest carved toes and iron hands through Victorian clockwork cleverness to the microprocessor knees and mind-controlled arms that are frankly astonishing. Along the way, you'll see how war sped things up, how materials reshaped bodies, and how the question, who owns your upgrade, went from sci-fi to everyday ethics. A quick note before we get rolling. We'll lean on well-documented breakthroughs and famous patents that shaped the field. Where the paperwork gets especially juicy, think landmark knees and neural interfaces. We'll talk about the core ideas those patents tried to nail down. But we won't drown you in legalese. We'll keep it human, mechanical, and delightfully practical. Ready to meet the most personal machines we've ever made? Let's walk. Pun very intended. Before we travel time, imagine you've got a modular prosthetic hand with 2 bonus attachments. What 2 tools or features would you choose? And should a company be allowed to patent those upgrades if they're attached to your body? Tell me your picks and your take. I'll share mine at the end. Ancient prosthetics to Victorian ingenuity. Sometimes the earliest solutions are so direct, they feel inevitable. You lose a toe, you carve a toe. But what looks simple is quietly sophisticated. Take ancient Egypt. Archaeologists found a wooden big toe fitted to a mummy from around 3,000 years ago. It wasn't just ceremonial. It had a curved underside and leather bindings, clearly used in life. Why a toe? Because the big toe is balance and push off. Replace it with something shaped right, and you can walk more naturally, wear sandals, live your life. That's function over flash. Biomechanics before biomechanics had a name. Meanwhile, medieval Europe gave us iron hands. Imposing, yes, but also surprisingly nimble. Some designs had sliding plates and spring-loaded fingers you could lock around a sword hilt or a quill. They were heavy and hot, but they mattered. They signaled, I'm still here. I can still do things. An iron hand could be status, armor, and a crude machine all at once. Fast forward to the early 1800s, and the line between watchmaker and limb maker all but disappears. Craftspeople start hiding springs, cables, and pulleys inside sculpted wood and leather. The goal? Natural motion that proves you're not just patched up, you're restored. Enter 1846, and an American inventor named Benjamin Franklin Palmer. His artificial leg becomes so popular that it's simply called the Palmer leg. This wasn't a dead stick. It mimicked the way a calf muscle and Achilles tendon store and release energy. The foot flexed. The knee moved smoothly. Codes and springs guided motion so your gait didn't scream prosthetic from a block away. And the marketing didn't hurt. Testimonials, pamphlets, demonstrations. Palmer didn't just sell a leg, he sold dignity and speed. What's so clever about these early devices isn't just the mechanics. It's the interface, the socket, the way machine meets flesh. Even in the 1800s, makers obsessed over where pressure falls, how skin breathes, how to stop chafing. If you've ever worn new shoes for 8 hours, you've caught a tiny glimpse of that problem. A prosthetic user faces it every day. By the late 19th century, we're seeing legs with adjustable ankles, hands with springy fingers, and even switchable attachments. The core question never changes. Can it bear weight, control contact, and feel natural. It's woodworking, metalworking, and ergonomics, long before either word was in vogue. War as accelerator. No one likes this part, but it's true. Every major conflict has pushed prosthetics forward, not out of glory, out of necessity. The American Civil War created an unprecedented population of amputees. Governments and charities started paying for limbs. Suddenly, the small workshop had a line out the door. That demand forced standardization. Prosthetists experimented with sockets and suspensions, straps, belts, laces, to keep limbs secure without torturing the wearer. The makers didn't have advanced plastics yet, so they relied on wood, leather, steel, and patience. Lots of fitting, lots of shaving and reshaping. Comfort meant compliance. If it hurt, you didn't wear it. By World War I, two ideas were maturing: the total contact socket and modular design. Instead of balancing on a bony stump inside a cup, the socket spread pressure across tolerant tissues. Pain went down, control went up. And if you could swap components, knees, feet, pylons, you could repair or upgrade without starting over. It's not glamorous, but it's huge. World War II and the decades after gave us materials: aluminum alloys, resins, and eventually high-strength thermoplastics. Lighter limbs mean less energy to move them, especially for above-knee amputees where every ounce matters. Plastics also mean you can heat, mold, and remold sockets to fit living, changing tissue. That's comfort you can literally shape. Then the 1960s brought the idea that muscles could talk to machines without cables. Myoelectric control burst out of labs and into clinics. The principle's elegant. When you voluntarily tense certain residual muscles, the electrical signal, an EMG, can be picked up by surface electrodes inside the socket. Amplify it, filter it, and you can command a motor to open or close a hand. No shoulder harness, no bow-like cable. Just a squeeze to open, a squeeze to close. It felt like the future, and for many, it still does. But myoelectric control came with its own headaches. Electrodes like good contact. Sweat, dust, and motion are their nemesis. Signal noise is real. Early hands were powerful but binary, open, close, without delicate proportional control. Still, the leap was enormous. For the first time, a user's own muscles were the remote control. Around the same time, socket science quietly kept evolving. The suction socket emerged for many above-knee users, a snug fit that creates negative pressure to hold a limb without straps. The benefit? Better proprioception, less pistoning, and when it fits right, a more part-of-me feel. Downsides? Skincare becomes a routine, and fit is everything. Gain or lose 5 pounds, and your socket lets you know. By the late 20th century, another quiet revolution was underway: dynamic response feet. These are composite feet, often made from carbon fiber, that store energy under load and release it at toe-off. Think of a bent archery bow that snaps straight as you push off. Users report the difference instantly. Walking feels springier, less like dragging, more like striding. Just as importantly, the feet can be tuned to different activities: walking, running, hiking, by shape and layup. So the war-driven sprint produced 3 pillars that today's bionics still stand on: interfaces that respect biology, materials that cheat physics, and control schemes that listen to the body instead of bullying it. Landmark IP and the rise of truly smart limbs. By the 1990s, the groundwork was laid. Then the microprocessors showed up. And everything changed. Let's start with the knee that made cybernetic feel practical. The C-Leg from Autobach. It's a microprocessor-controlled knee that continuously reads sensors, angle, speed, load, and adjusts hydraulic resistance in real time. Translation: if you stumble, it stiffens to catch you. If you walk slower, it smooths out swing. If you tackle a ramp or a hillside, it adapts so you don't feel like you're wearing a metronome. The idea isn't to walk for you, it's to get out of your way. Why did this matter so much? Because walking isn't a repeatable loop. Every step is different. Microprocessors let the knee be a partner, coaching when needed, invisible when not. The patents around these systems tend to focus on sensing strategies and control algorithms that coordinate stance and swing phases while maintaining stability. In other words, the secret sauce is how it decides what to do and how fast it does it. Then, there's the arm with a nickname straight out of sci-fi, the Deca Luke arm. Born from defense funding and clinical grit, it aimed to restore multiple degrees of motion at once. Wrist rotation, wrist flexion, and extension, elbow function, multiple grip patterns, even fine motor tasks. The control options are flexible, foot-mounted inertial sensors, muscle signals, or even neural inputs in some research settings. What's radical here isn't just dexterity. It's the design principle that a prosthesis should be modular, serviceable, and upgradable, like a high-end tool system. That mindset shows up in the intellectual property too. Mechanical architectures for compact joints, compliant transmissions, and control interfaces that swap without ripping out the whole system. Now, let's talk about something that flips an age-old compromise: osseointegration. Instead of suspending a prosthesis from soft tissue, osseointegration implants a titanium fixture directly into the remaining bone. The limb then connects to that fixture through the skin. Benefits? You feel forces through your skeleton. Better proprioception, more precise control, less soft tissue pain, and no socket to sweat through. The trade-offs are serious: surgical risks, infection at the skin interface, and a long rehabilitation. But for people who can't tolerate sockets, it can be life-changing. The patents in this space often center on implant shape, surface treatments that invite bone growth, and connectors that manage loads while protecting tissue. Layered on top of these hardware revolutions is a control revolution. Multi-channel myoelectric systems now decode not just open or close, but which grip you want. Pattern recognition looks across a landscape of muscle signals and maps them to functions. Some systems let you train the prosthesis on your intent, the way you'd train a voice assistant, only more personal. The goal: make control intuitive enough that you stop thinking about the device and start thinking about the task. And this is where things get almost spooky in a good way. Neural interfaces are stepping in. Peripheral nerve interfaces aim to read signals directly from nerves to control prosthetic fingers. Others stimulate nerves to send sensation back: pressure, vibration, even texture, so you don't have to watch your hand to know you're holding a grape. With invasive brain-computer interfaces, researchers have shown high DOF arm control with closed-loop touch feedback. It's early, it's experimental, but it's not hypothetical anymore. As the tech got smarter, the business did too. Companies filed and defended patents covering everything from how a microprocessor knee knows you're on a staircase to how a myoelectric hand switches grip patterns without false triggers. In some ways, that's great. Competition breeds choice. Patents force clarity. What's the invention exactly? In other ways, we bump into ethical questions. If your independence depends on a patented feature, what happens when licensing gets messy? That's why a quiet, parallel movement has been growing: open source limbs and community-driven design. Think 3D printed hands for kids who outgrow expensive devices every year. Think common file formats, hackable control boards, and modular sockets you can repair locally. None of that replaces high-end bionics, but it makes the baseline better and the experimentation faster. In open projects, you'll see iterative improvements shared like recipes: a better wrist bearing, a more comfortable liner, a low-cost EMG amplifier. The IP is a GitHub repo. In the best world, these threads, landmark, carefully protected innovations and fast, open community hacks, don't fight. They cross-pollinate. A clinic-level device might adopt an open protocol that lets third-party apps fine-tune gait. A maker project might borrow a materials trick from an academic paper, and suddenly thousands of users feel less skin shear. Meanwhile, we're learning that smart isn't just electronics. It's the whole system. Suspension that changes with your activity, feet that adapt to terrain, batteries that recharge wirelessly, waterproofing that lets you shower without a plastic bag mallet. And yes, machine learning is creeping in. Your knee notices your habits and tunes itself for Monday's commute versus Saturday's hike. Your arm updates grip speed based on how often you fumble a coffee cup. Nothing in the loop replaces you. It just amplifies you. 4 threads tie this whole story together. Interfaces are destiny. Whether it's a leather strap, a suction socket, or a titanium implant, comfort and connection decide if a device becomes a body part or a boat anchor. Materials matter as much as mechanics. From wood and iron to carbon fiber and medical-grade silicones, each leap in matter changed what was possible. Control keeps marching inward. From harnesses to EMG to nerves and cortex, we keep moving the conversation closer to the brain. The closer we listen, the more the device disappears. Patents can both protect and gatekeep. They reward the risky work of inventing microprocessor knees and neural feedback. But they also raise questions when features feel like necessities rather than luxuries. And tying it all together is culture. Dignity and identity show up in every era, from an Egyptian big toe carefully carved for sandals to a 21st century runner who swaps feet to chase a personal best. So, could you patent a body part? Legally, you can't patent a naturally occurring limb, but you can patent the machines that replace, restore, or upgrade one. And for better or worse, we have. The good versions of that story look like partnership. Engineers, clinicians, and users co-designing features that read your intent, protect your skin, and give you back the rhythm of walking or the nuance of a handshake. The bad versions happen when access depends on the luck of your insurance, or when upgrade starts to mean paywall on your body. I'm optimistic, though. The long sweep from a carved wooden toe to knees that sense your stumble shows a field that listens, iterates, and centers the person. The coolest tech in prosthetics isn't a chip or a motor. It's empathy expressed as engineering. And that, to me, is the most human invention of all. Back to that thought experiment. You've got a modular prosthetic hand and 2 bonus attachments. My picks? A gentle, tactile sensor tip for precise feedback, and a quick swap universal driver so I can fix a bike on the fly. As for patents, I'm fine with companies protecting the how, as long as the what, basic function and compatibility, stays open. Your turn. What 2 attachments are you picking? And should those be patentable if you're attached to you? Drop your picks and your reasoning in the comments. I'll be reading and featuring the cleverest combos.